expectation and variance of continuous random variable. So in the previous session we have seen that expectation for the discrete random variable is denoted by this symbol, and it is equal to the summation of product of the values that random variable can take and the respective probabilities that we're going to get from the PMF table. And we have also seen that for the discrete random variable, variance of that random variable is denoted by this symbol, and it can also be denoted by this symbol, and the formula to calculate the variance for the discrete random variable was equal to expectation of whole square of x minus nu x, where this x is the values that the random variable x can take, that the random variable capital X can take, and this nu x is the expectation of that random variable. In the previous session we have also discussed the properties of expectation and properties of variance, and we have also practiced some example on these formulas and properties to clarify our concepts. In today's session, we will be discussing expectation and variance of continuous random variable, and we will also see that for the variance of the random variable, there is another formula which is equal to expectation of x square minus expectation of x whole square, where this x is a random variable for which we are calculating the variance. We will see that this formula is derived from this formula itself, and this is also useful in some of the questions instead of this formula. So now let us start with our today's topic, which is expectation and variance of continuous random variable. So expected value, or I can say mean value of continuous random variable. So it is denoted by E of x, and the formula to calculate the expectation for the continuous random variable is integration from minus infinity to plus infinity of product of x and the PDF values. Here this x is the real number values that the capital random variable x can take, and this is the corresponding PDF values. This formula is quite similar to this formula which we have seen in the previous session. The only difference is that at the place of summation, here we have integration, and at place of PMF, here we have PDF values. So let us quickly take an example to understand this formula. So this is the example. Here in this example, for the random variable x, a PDF table is given to us, and here in the A part we need to calculate the expectation of the random variable. So we can calculate expectation of this random variable using the formula that we have just seen. So let me first write the formula, which is equal to integration from minus infinity to infinity multiplication of x with the PDF values. Now here you can see that the PDF values only exist between 0 to 1 interval. It is 0 for all other values. So I can break this in the interval first from minus infinity to 0 x, and here the PDF value is 0. In this range the PDF value is 0, and now I will integrate it from 0 to 1, and in this range the PDF value is 1. and now I will integrate from 1 to infinity. Again in this range the PDF value will be 0. So it is simply equal to integration from 0 to 1 of x dx, which is this expression because these two expressions were 0. Now if we will integrate this, we are going to get x square upon 2, and the range is from 1 to 0. Putting the limits, you are going to get 1 upon 2 minus 0, which is finally equal to 1 upon 2. So in this particular case, the expectation of x is equal to 1 by 2. Now I hope that this example is clear to you. Now if you are confused that how I break this, so let me explain this to those who are confused in this part. We know that we need to integrate from minus infinity to infinity, and the different real number values that are visible to us in the range of PDF are 0 and 1 only. So I will mark 0 and 1 on this number line. And now you can see that the number line is divided into 3 different regions. The first one is minus infinity to 0, the second one is 0 to 1, and the third one is from 1 to infinity. So in this way you can break your integral in these 3 parts. If in the PDF table is like this, for example, let's say it is 1 to 1 in the range 0x and 1, 2 in the range 1 to 2, and 0 otherwise. Then the PDF can be break in the 4 parts, which is 0, 1, 2. From the range side, I have put the different real number values that I can see and put them on the number line, and then I can break the number line in different regions. So if the PDF table is like this, then you have broken your integral in these 4 different regions. Now I hope that this is clear to you that how I broke this integral into these 3 parts. So now let us move on to our discussion of expectation. So now let us discuss properties of expectation. The first property of expectation is expectation of AX, where A is a constant and X is a random variable. A is the constant and X is a random variable is equal to A of EX. If I will link this to the previous example where we have calculated E of x is equal to half, if someone has asked you expectation of 2x, then it would be equal to twice of expectation of x, which will come out to be twice of half equal to 1. Now the second property of expectation operator is expectation of sum of random variable, where x is a random variable, y is a random variable, is equal to e of x plus e of y. So for example, if you have 2 random variable x and y and you know the expectation of these random variable individually, like expectation of x, you know that is equal to half, and let us assume that there is another random variable y whose expectation is equal to, let's say, 1 by 3. And now if someone asks you to calculate expectation of x plus y, then using this property you can say that it would be equal to sum of these two. which is 1 by 2 plus 1 by 3, which will come out to be 5 by 6. And this property can be extended to any number of random variable. If you have, let's say, 4 random variable x, y, z and w, these all are random variables, then it will be equal to expectation of x plus expectation of y plus expectation of z plus expectation of w. Now the third property of expectation operator is expectation for constant is equal to constant. Where is a constant? So if I will give you example for this, then if you will find expectation of any constant number, like if you will find expectation of 7, now we know that 7 is a constant, then using this property we can say that expectation of 7 will be equal to 7. If we will find expectation of 5, then it will be equal to 5. Similarly, for any constant number, if you will find its expectation, then it will be equal to that constant number only. Now, if I will take all these three properties, then I can generalize them as expectation of ax plus b is equal to a of ex plus b, where a and b are constant and x is a random variable. Now this is derived in the following manner, that expectation of ax plus b is equal to expectation of ax and expectation of b. Now expectation of ax using this property is equal to a into expectation of x, and expectation of a constant is equal to constant. And now we have derived this. So now let us move on to the fourth property of expectation. The fourth property of expectation operator says that expectation of any function of random variable, here gx is a function of random variable capital X, is equal to minus infinity to infinity that function whose expectation we are finding here multiplied by the respective PDF values. Now in the previous session we have seen this property for the discrete random variable, and we have practiced an example on this where we need to find the expectation of an expression of random variable x, but I have not mentioned this as a property. Now let us practice an example on this property for the continuous random variable so that this property gets clear to you. Now in the B part of the previous question, we need to find the expectation of x square. Now we know that x square is a function of x. So we can use the property that we just studied to find this. Now we need to find the expectation of x square. Here gx is equal to x square, and our property says that when we need to find the expectation of the function of random variable, then that was equal to integration from minus infinity to plus infinity of product of that function into PDF values. Now here the function is equal to x square, so it can be written as minus infinity to infinity integration. The function is x square, and then after function we use to take its product with the respective PDF values. Now again I will break this integral in the three parts. Minus infinity to 0, which will be x square 0 dx, 0 to 1 x square 1 dx, 1 to infinity x square 0 dx. Here I have just broke this integral in three parts like we have done in the previous A part. So this should be clear to you. The only difference is that at place of random variable x, I just have put its function x square. Now simply this will come here because these two are 0. So it will be integration from 0 to 1 x square dx, and integration of x square is x cubed by 3, and limits are 1 and 0. So putting the limits, we will get 1 by 3. So clearly expectation of x square is equal to 1 by 3. So now let us see the fifth property of expectation operator. The fifth property of expectation operator says that if you will find the expectation of random variable minus its expectation, then you will get 0. That is, if I will give you an example to make you understand this, if in the previous question where we have find that expectation of the random variable was equal to half. So if you will use this property and find the expectation of, from question 1a we are taking this example and we are finding the expectation of x minus its expectation, which we have seen that comes out to be half. So expectation of x minus half will be equal to 0. This can be simply understand using the property that we have seen earlier. We know that expectation of ax plus b can be written as a into expectation of x plus b. Now expectation of x minus half can be written as expectation of x plus expectation of minus half. Now expectation of x will be expectation of x, and expectation of minus half will be equal to minus half, and we have seen that expectation of x is equal to half, so it would be half minus half is equal to 0. So this property is basically derived from the generalized one that we have seen earlier. Variance of continuous random variable. So in case of discrete random variable, we have seen that variance of discrete random variable was equal to expectation of this expression. So similarly in the case of continuous random variable, we can write that variance of random variable x is equal to expectation of this expression only. Now the difference in the case of continuous random variable comes in finding the expectation, because in discrete random variable we use summation and PMF to calculate expectation, but in case of continuous random variable, as we have seen, we used to calculate expectation using integration and PDF values. So its expectation will be equal to, using this formula, here the function is this in the expectation operator. So I will put this function here only. at the place of gx in the integral and put the PDF values. So this is a formula to calculate the variance of the continuous random variable. Now, as I have told you, there is another useful formula to calculate variance, which is equal to variance of a random variable is equal to expectation of x square minus expectation of x whole square, where x is a random variable whose variance we are calculating. So let us see that how this formula is derived from this formula. So this is formula 2, you can say, and this is formula 1, or you can say this is property 1 and this is property 2. So now let us see derivation, that how from formula 1 we reach formula 2. So earlier we have in the beginning variance of x is equal to integration from minus infinity to infinity of this expression, where this nu max is the expectation of random variable. Don't get confused in nu max and ex. We know that ex and nu max both are expectation of random variable, or you can say both denotes expectation of random variable. So now let us open this square. We will have minus infinity to infinity integration x square plus nu x square minus twice of x nu x, and here we have PDF. So now this can be written as integration from minus infinity to infinity x square into PDF values plus integration from minus infinity to infinity nu x square into respective PDF values, and integration from minus infinity to infinity minus twice of x into nu x into PDF values. So this is what we have got from this. So now, using the property that we have studied earlier, this expectation of gx, that is function of x, is equal to minus infinity to infinity integration of that function multiplied by respective PDF values. We can see that here at the place of gx in integration we have x square, so it can be simply seen that here the gx function is x square. So here gx is equal to x square. So it can be simply using this property in reverse direction, we can write expectation of x square. And now if we will deal with this part, then we know that nu x whole square. Now nu x, expectation of any random variable, is always constant. Like in previous example, when we have find the expectation of random variable x, then we have got expectation of that random variable equal to half. So we know that the expectation of any random variable is constant. So we will bring this expectation square outside this integration and we will write it as it is. Again in this part -2 and this new max is constant, so we will also bring this outside this integration. Now from the property of PDF we know that the integration of PDF from -infinity to infinity is equal to 1. So this integration will come out to be 1 using the PDF property of PDF. We have also seen this property when we have discussed PDF in the previous lectures. Now we have just seen the starting of the session that this is the formula or the property to calculate the expectation of the random variable. So it can be simply written as expectation of x. Now we also know that this new x is also expectation of x, and this ex is also the expectation of x. These are the two symbols which denotes expectation of x, so they can be used interchangeably. Now this can be solved as expectation of x square minus new x whole square, which is in term expectation of x. So this can be simply written as expectation of x whole square, and here at this step we have derived our required property or the required formula to calculate the variance of random variable, and you must note that this formula is valid for both discrete and continuous random variables. You can use this formula to calculate the variance of discrete random variables also. So now let us move on to our previous question so that we can apply this formula and clarify our concepts related to variance of continuous random variable. So this was a question with which we were dealing. We have solved its A and B part. Now we will move on to the C part where we need to calculate the variance of the random variable x. Now I forgot to mention earlier that this is another symbol for variance of x. So now let us calculate this. Now in the C part we need to calculate variance of random variable x. Now using the formula that we have just derived, I can write that it is equal to expectation of x square minus expectation of x whole square. And in the B part we have calculated expectation of x square, which comes out to be 1 by 3. And in the A part we have calculated expectation of x, which was come out to be half. So it is equal to square of half, which is equal to 1 by 3 minus 1 by 4, which will come out to be 1 by 12. So this is our variance of random variable x. Now to clarify To check this, you can also use the another formula to calculate this, which is equal to integration of minus infinity to infinity x minus nu x whole square into PDF values. Using this formula, we will arrive to the same answer. Now you can yourself check this to get the same result, which will come out to be 1 by 12. Now let us see properties of variance. The first property of variance is variance of AX, where A is a constant and X is a random variable, is equal to A square into variance of X. Like in previous example, if someone asks you variance of 2x, then it will be equal to 2 square into variance of x. And as we have seen that the variance was equal to 1 by 12. So solving this, you have got 1 by 3. So if someone has asked you variance of 2x, then using this property, you can tell that variance of 2x is equal to 1 by 3. Now the second property of variance is that variance of a constant number is equal to 0. Here b is a constant. For example, variance of 2 will be equal to 0. Variance of 7 will be equal to 0. Similarly, if you will find the variance Similarly, for any constant number, the variance will be equal to 0. Now, using these two properties collectively, I can write that variance of AX plus B is equal to variance of AX plus variance of B, which in terms is equal to A square into variance of x plus 0, coming out to be A square into variance of x. Now let us move on to the another property, which is variance of x is equal to expectation of x square minus expectation of x whole square. We have also just derived this property. Now the another thing that you must note about variance is variance of x plus y, where x and y both are random variable, is not equal to variance of x plus variance of y. This is related to covariance of x and y, which we will see in the upcoming sessions. But for now, you must remember that variance of x plus y is not equal to the individual sum of variance of x plus variance of y. Now, standard deviation of random variable. It is denoted by the symbol sigma x. And now here you must note that the standard deviation is equal to root of variance equal to root of sigma square x, which will come out to be sigma x. Now if someone asks you to calculate the standard deviation of random variable, then first you will find its variance and then take under root of that to get your respective answer. So moving on to our previous question that we have taken earlier. Question in the D part, we need to find the standard deviation of the random variable x. Now in the D part, we need to find the standard deviation of random variable x, and we know that it is equal to under root of variance of random variable x, and we have already calculated the variance of x as 1 by 12, so its standard deviation is equal to 1 by 12, and we can write 1 by 2 into under root 3. So this is the standard deviation of random variable. So now I hope that this discussion of expectation and variance of continuous random variable is clear to you.